Good morning, good afternoon, good evening, depending on where you are in the world. My name is Brian Anthony. I'll be your host for today, our next Nano Explorations seminar series, highlighting our phenomenal students at MIT. Just as a reminder, this seminar is being recorded. If you can please keep your videos off to save bandwidth. And at the end, we'll take questions, and you can please either raise your hand or enter into the chat, and we will get going. So it's my pleasure to not introduce our speaker yet. I'll first introduce our speaker's advisor, Professor of Chemistry, Muji Buendi. I'll turn it over to you, and please introduce Jason for everybody else.
Okay, well, thank you, Brian. It's really my pleasure to introduce Jason to give this talk, this virtual presentation from his cell in a hotel in Seoul, where he's been quarantining for the last week or so. Jason was a student in my group for about 5 years, worked on a number of projects, a wide range of different projects, and he met up with a friend who was doing a postdoc with Tony Buenasisi's group, and they started working together on the side project on Perovskite solar cells. And the two of them, that really took off in a way that I could not have imagined. And that's what he's going to be talking to you about. And I'll let him, I won't give you punchlines, I'll just let him tell you that story of that particular project that he worked on while he was at MIT. And I know he's going to be continuing work in that direction, and I expect that many great things to come out of the next few years from him in that direction. So Jason, it's all yours.
Thank you, Munji. I will share my screen now. Yeah. So my name is Jason. I'm a student in Munji Buendi's group, and the topic for today's webinar is pushing the efficiency limit of lead halide perovskite solar cell. So first of all, what is perovskite? So broadly speaking, perovskite is a type of mineral that follows the chemical or the crystal structure of calcium titanium oxide with the chemical formula of ABX3. Now, if we zoom in with the microscope, we'll see that it has the following crystal structure. And the type of perovskite that we're interested in for various optoelectronic properties devices is a lead halide perovskite, where the A side cation, such as methylammonium or formamidinium, is surrounded by an octahedral cage composed of lead and halide. And with all that together, it forms a lead halide perovskite. So some of the examples include formamidinium lead iodide, which is widely used for photovoltaic applications, methylammonium lead bromide, which is used for making efficient light-emitting diodes, and there's also a mixed halide case, such as cesium lead bromide iodide. Then the question is, why do we study lead halide perovskite? So first is processing. So compared to more traditional semiconductors, which requires extremely high temperatures for making efficient devices, perovskite solar cells can be processed at low temperature. And it is also a solution processable, which makes them a scale-up friendly device structure. Also, perovskites are known to be tunable in bandgap by changing the composition or its stoichiometry. So for example, by changing its halide stoichiometry, we can tune its bandgap across the entire visible wavelength range, where a lot of the interesting applications are. And these applications range from tandem photovoltaics to LEDs. Also, they have ideal intrinsic optoelectronic properties, such as a low binding energy, high absorption cross-section, and also a long carrier lifetime. They're also known to be defect tolerant, which check all the boxes for making highly efficient devices. Now, with all of that together, they can be put into a lightweight form factor, providing one of the highest power per weight. And because of that, they can be used in diverse applications, for example, to power a lightweight drone or an aircraft, shown as in this picture. Here, I want to introduce some important milestones that have happened in the Perovskite Solar Cel community. First, the concept of using perovskite as a light harvesting material was first introduced in 2009 when researchers grew a tiny perovskite crystallite onto a titanium dioxide scaffold. And this is what this was prepared to be used as a dye-sensitized solar cell. On the left, I'm showing a JV curve from this work, and they report an efficiency of around 3%. Afterwards, a solid-state perovskite based on a mesoporous structure was developed. Now, a solid-state solar cell operates by having an active layer, such as a perovskite active layer, sandwiched between two charge selective transport layers, such as the electron transport layer, or ETL, and a hole transport layer, HTL. And the role of these charge transport layer is to efficiently extract the charges from the perovskite layer before they recombine. Now, with the solid state structure, it resulted in improved light collection and also carrier extraction, pushing the efficiency to about 10%. However, they suffered from inhomogeneity in films and also the poor film quality, such as pinholes or incomplete coverage. So to overcome this, a method called solvent engineering was developed, where the perovskite crystallite was precipitated in situ during fabrication using non-solvents. And this resulted in improved film morphology and coverage as shown by this SCM image below. And with that, the efficiency has rose to about 15%. However, this method still suffered from defects within the bulk and also in the grain boundary. Currently, a lot of the effort has gone into composition engineering, where a small amount of additives such as metal cations or various composition is added into the perovskite bulk to improve its bulk film property and also device stability, where on the right I'm showing a efficiency tracking over a long period of time. And with the addition of a small amount of cesium cation, there is an increase, or there is improvement in the stability as shown by this maintaining of its efficiency. And this resulted in efficiency of around 20%. Then the question is, how do we further improve the device performance? Now, in order to devise a plan to further improve the device performance, we first need to see where the efficiency deficit is coming from. On the left, I'm showing a plot of PCE, which is the power conversion efficiency, or how efficient a solar cell can convert sunlight into electricity, and band gap. And this black trace is the theoretical maximum a single junction solar cell can have, which is also known as the Shockley-Queisser limit or the SQ limit. Now, the perovskite usually has a band gap of around 1.5 to 1.6, which means that they have a maximum efficiency of around 30 or 31%. Then the question is, where is this efficiency deficit coming from? We can divide the device metric into two parts. One is the JSC, which is related to the light management. And then the second is the product of the VOC and the fill factor, which is related to the carrier management. Now, perovskite is actually doing really well on the light management aspect. However, we see that there is a significant deficit on the carrier management side. And a strategy called a surface passivation or interface passivation can be implemented to improve the carrier management. So what is an interface passivation and why is it important? For a colloidal semiconductor, such as quantum dots or nanocrystal, if we have an exposed surface, it can act as a recombination center that results in a poor photoluminescence efficiency. However, by introducing a proper ligand system or an inorganic shell, we often see an improvement in the photoluminescence property, and that is due to passivation of these trap states. For a crystalline semiconductor, such as crystalline silicon, by passivating the dangly bonds, we also see an improvement in the photovoltaic performance. Then the question is, can we use perovskite as a passivation layer? Because as I've mentioned towards the beginning of this presentation, perovskite has numerous traits that allows them to be used for making highly efficient devices. Now, a strategy that has worked really well in colloidal semiconductors, such as quantum dots, is to overcoat the core with a shell material that has a wider band gap. Now, can we translate the same idea to a bulk perovskite, where we add a thin layer of a passivating layer? Now, then this passivating layer has to be a wide band gap, needs to be chemically stable, and also has to be defect tolerant. Now, there is a subclass of perovskite called a 2D perovskite or layered perovskite that actually satisfy all those requirements. Now, then what is a 2D perovskite? Now, compared to the 3D perovskite, which has an extended, infinitely long extended network, the 2D perovskites are formed by having a layer of bulky organic cations between these sheets of perovskite layers. And going from an n value of infinity, where the n value is the number of octahedral layer between the organic cations, going from a high value to a low value, we see an increase in the band gap noted by this blue shift in the absorbance profile. So the layer 2D perovskite provides the increase in the band gap, and also they are reported to have better phase stability, and that is because perovskite is known to be a soft material, and you could think of these organic cations sort of blocking these crystal structures in place, thus providing a better crystal phase stability. So we can design a device structure such as following, and we call it the 3D 2D heterostructure perovskite solar cell, where there is a thin layer of 2D perovskite that is responsible for interface passivation and also improved stability. And this bulk 3D perovskite is responsible for high absorption and also high device efficiency. So then how does one go about making such a device? We would first start up with a transparent conductive oxide, followed by the deposition of the electron transport layer, the perovskite layer, the passivation layer, and finish off with the whole transport layer and the metal contact. However, with the fabrication being done in a solution processing manner, a poor fabrication protocol could lead to formation of unwanted byproducts, which is shown as this thin layer, yellow layer. And we in fact learned that a poor passivation strategy does lead to interface destabilization, which undermines the benefit that you get from a passivation. And that is because perovskites are known to be easy to make and easy to break. So broadly speaking, perovskites have two crystal phases. One is the alpha phase, which is also known as the black phase, and the other is the delta phase, which is also known as the yellow phase. And these black and yellow are assigned because they physically have a color black, and the other one looks yellow. The alpha perovskite, or the alpha phase, is a cubic phase, which is known to be an efficient light absorber. However, the delta phase, which is an orthorhombic phase, is reported to be a detrimental trap state and also a carrier recombination center. Now, unfortunately, at room temperature, the thermodynamically preferred state is the delta phase, which means a perovskite that has been stabilized to an alpha phase can readily convert to delta phase when it is exposed to destabilizing environments. So this justifies developing a delicate surface passivation strategy. Now, with the device fabrication being done in solution processing manner, we've decided to understand the effect of solvent orthogonality on the passivation. On the left, I'm showing a solubility of the 3D perovskite precursor and the 2D perovskite precursor going from low to high. Here, the solvents listed inside this black box are solvents that are often used for solvent engineering, which is used to precipitate the perovskite crystals during fabrication. And that is because they have low solubility for both the 2D perovskite and also 3D perovskite. Now, the solvents listed in this blue box are solvents that are often used to prepare the perovskite precursor because they have, the perovskite solution, because they have a high solubility. And we discovered that chloroform is uniquely positioned, that it has a low solubility against the 3D perovskite, but a high solubility against the 2D perovskite precursor. And this trend generally follows the increase in polarity. And of those solvents, isopropyl alcohol, or IPA, is the most widely used solvent for post-processing. And we're going to call this method, the method of using IPA, the conventional method. We also did some quantitative analysis by measuring the solubility. First, the solubility of bromadium iodide, which is a 3D perovskite precursor. Its solubility in IPA is around 200 milligrams per mil. And the solubility of C6Br, which is the passivating agent, or hexylammonium bromide, its solubility in IPA is around 500 milligrams per mil. Now, in an ideal scenario for post-processing, you want the solubility of FAI to be as low as possible and C6Br to be as high as possible. And we, in fact, see that in the case of chloroform, where the difference is basically a night and day. So FAI is essentially insoluble in chloroform, whereas C6Br solubility exceeds a gram per mil. So this unique combination of using chloroform with C6Br provides the ideal discrepancy in solubility for post-processing. And we're going to call this method selective precursor dissolution strategy compared to the conventional method. And here I'm going to demonstrate its effect by showing photograph of phonolmadium lead iodide perovskite powder dispersed in two different post-processing solvents overnight. So on the left is the powder dispersed in chloroform, and you see that it retains its black color, which means it hasn't undergone chemical decomposition or phase change. And on the right is the perovskite powder dispersed in isopropyl alcohol, or the conventional method solvent. And we see that for the IPA, the perovskite decompose into its precursors, which is lead iodide and phonolmadium iodide, where lead iodide has a yellow color And also the delta phase or the yellow phase also has a yellow color. We perform X-ray diffraction measurements to have a better understanding of its change in crystal structure. So the black trace I'm showing is the diffraction pattern for the 3D bulk perovskite, or the 3D control, where the two peaks correspond to lead iodide and the 100 plane of the 3D perovskite. The two traces shown in blue and red are the 3D heterostructure prepared using the conventional method and the SPD strategy. Here we see that with the heterostructure, there is an evolution of new peaks in the lower 2 theta range, suggesting a formation of a crystal structure with a larger lattice constant. And we assign this to the 2D perovskites. We also synthesize pristine 2D perovskites to have a better understanding of its composition, and we decided that it matches nicely with this following composition. Also, another thing that stands out is that with the SPD strategy, the diffraction peaks that correspond to the 2D perovskite, which is these three here, the intensity is much more intense for the SPD strategy compared to conventional method, suggesting more efficient in situ synthesis and higher quality. And also, we were able to confirm its chemical composition. Now, if we zoom in to this specific range, where once again the conventional method is shown in blue trace, and the SPD strategy is shown in red trace, we see that there is a detectable amount of delta phase for the conventional method, suggesting that the SPD strategy suppresses the formation of the delta phase. So then how does the SPD strategy affect thin film properties? We first perform time-resolved photoluminescence to have a better understanding of its carrier dynamic. And by fitting the long component to a mono-exponential, we see that there is about a 3-fold improvement in the carrier lifetime. And this can be attributed to a reduced non-radiative recombination. We also perform Kelvin probe force microscopy to probe its surface potential of the 3D control and the 2D heterostructure. And by analyzing the coefficient of variation, we learned that there is a reduced potential distribution with the 2D heterostructure compared to the 3D control. And we assign this to be the result of grain and grain boundary passivation. So how does the SPD strategy or the 2D perovskite passivation using SPD strategy affect the device performance? On the left, I'm showing a JV curve of the 3D control and the 3D heterostructure, where the dotted line is the average and the shaded area is the distribution. And on the right, I'm showing the device statistics of 4 device metrics: the VOC, the JSC, the fill factor, and the power conversion efficiency. And we see most of the improvements from the open circuit voltage and the fill factor, which is responsible for the overall improvement in the power conversion efficiency. Also, starting a couple of years ago, there's been a big debate in the community as to how we can better accurately determine the efficiency of a perovskite solar cell. And that is because perovskite solar cell exhibit a phenomenon called hysteresis, which is the discrepancy between the forward sweep and the reverse sweep in a conventional JV sweep. And the maximum power point, which is where the solar cell generates the highest power, or also where the solar cell will be operated in, is thought to be situated between the two sweeps. Now, the advantage of using conventional JV sweep, which is just sweeping the voltage and measuring the current or the current density, the advantage is that it is simple and fast. However, the downside is that the power conversion efficiency that is measured or extracted is sweep rate sensitive or sweep rate dependent. And as a result, it is difficult to extract the true efficiency. Now, a method that was adopted and is now being widely used is called a quasi-steady state method, where instead of sweeping the voltage, we are stepping the voltage at a certain interval. And at each voltage point, we are waiting long enough for the current to stabilize within a certain range, or the certain, window. Now, the advantage of using the quasi-steady state method is that it is sweep rate independent, and also we're able to extract the stabilized power. The downside is that it is highly time consuming. So a typical measurement takes about 30 minutes compared to less than a minute for a conventional JV sweep, which means that an unstable device will not survive this more robust measurement and can degrade during testing. So what is the QSS result, or the quasi-steady state measurement of the 3D 2D perovskite solar cell that was prepared using the SPD strategy? So we sent our device to a credit testing center for certification purpose, and we were able to pass the test with the certified steady state efficiency of 22.6%. And this was the highest reported value at the time. And also encouraged by the high open circuit voltage, we decided to characterize its electroluminescence efficiency. And this is relevant for many reasons. And also Eli Yablonovich, a professor at UC Berkeley, has once said, a great solar cell has to be a great LED, because an open circuit voltage is related to its radiative efficiency, and the radiative efficiency is also related to the efficiency of the electroluminescence. So on the left, I'm showing electroluminescence spectrum of the perovskite solar cell operating under forward bias as a function of voltage. And the image on the left is an actual perovskite solar cell emitting a visible light operating under forward bias. On the right, I'm showing a curve of radiance, which is how bright it is, and EQE, which is the electroluminescence efficiency versus voltage. Here, the dotted line is the 3D control, and the solid line is the 3D 2D heterostructure. And we see that there is about a threefold improvement in the EL efficiency and also brightness for the heterostructure compared to the 3D control. So with the SPD strategy developed for 2D perovskite passivation, we were able to achieve a higher quality 2D perovskite passivation layer along with a stabilized interface. And this resulted in a high power conversion efficiency and also a low VOC loss, where the lower the VOC loss, the higher the radiative efficiency. And this is also supported by a high electroluminescence efficiency. And here I want to introduce the current sort of state of the art in the perovskite solar cell community. First, the unit cell record, where the unit cell is usually defined as areas less than a square centimeter, is currently at 25.2 for them. And it is set by work collaboration coming out of MIT, including our group, and CRIT, which is a national lab in South Korea. And currently there is another record that is a statistical tie with our current record. The record efficiency for module is currently at 16%, and the dimension for the module is right now 30 centimeter by 30 centimeter. And there's also a report of a perovskite solar cell that exhibits stability up to a year. Unfortunately, all of these amazing achievements are independent. So I think moving forward, we need to develop a perovskite solar cell that is not only efficient, but also large in area and stable. So to do that, we need to tackle some of the remaining challenges. So first is the deficit in the module efficiency. So on the left, I'm showing power conversion efficiency of silicon, gallium arsenide, and perovskite solar cell with the unit cell and module shown as these two columns. Now, for the silicon and gallium arsenide, the efficiency of the module is not too far behind that of the unit cell. However, when it comes to perovskite solar cell, the efficiency of the module is significantly lower than that of the unit cell. And the question is, how to improve the large area fabrication? In order to do this, we need to develop a deposition method that is tailored towards perovskite. And that is because perovskite is unique in that it requires an in situ crystal growth. And this has to be optimized and developed and researched to improve the film homogeneity, where sort of as represented by these different shades or colors, we need to improve the deposition method so that they have a uniform quality and also physical, I guess, properties. The other remaining challenge is the efficiency lifetime. So for a silicon photovoltaic, the T80, which is the time it takes for a solar cell to reach 80% of its initial efficiency, is usually around 20 to 25 years. However, compared to that, currently at a lab scale, the perovskite solar cell, the T80 of the ones that are reported is significantly shorter than a year. So in order to improve this, we need to find a way to prevent degradation during operating conditions such as electrical bias, light, and also temperature. To do that, we need to understand the degradation mechanism. So one of the mechanisms that is known is ion migration, where let's say this is the perovskite active layer, and you have two different contacts under external stimulus, such as electrical bias or light. The mobile ions within the perovskite migrate to its, I guess, corresponding contacts depending on its charge. The second is the composition stability, where there is a trade-off between efficiency and stability. For example, cations such as formamidinium and methylammonium based perovskites are used to make efficient devices. However, they're not as stable. Whereas on the other side, these metal halide, these metal based perovskites are stable, but they don't result in efficient devices. So these two are sort of the main degradation mechanism that has been reported that needs to be studied on future works. So with that, I'd like to thank the group, the Buendia group, the collaborators, the funding agencies, and thank you for your attention, and I'll be happy to take any questions.
Jason, thank you very much. I send you the real clap and the virtual clap here on the icons. So please, participants, if you have questions, please either raise your hand or type in the chat. I have one question that's was chatted to me as you were going. If I sort of paraphrase it correctly, I think the question is related to what are the other scale-up issues in terms of cost of materials, supply chain issues relative to other photovoltaic material choices?
Okay. Can you repeat that question again? I just want to make sure that I got it correct.
Yeah, certainly. The question was around the availability of materials and the cost of materials And I think they're also asking in the current COVID environment where supply chains are potentially disrupted a little bit. So I think it's asking, you know, how commonly available are the materials that you'll need, the perovskite materials, the raw materials to make solar cells.
So if we just narrow the focus on, or narrow the discussion for the perovskite active layer, currently the argument is that at least for the lead halide based perovskites, the precursor is really cheap, or at least it's sort of, you know, earth abundant. So the common argument would be that it won't be expensive to source it. However, there is sort of this caveat that follows, and that is that lead is, at least at the moment, not ideal for, you know, many purposes or many reasons also. And if you want to go to a alternative, I guess, like a lead alternative, then it is more difficult to source those chemicals, as they are not as, you know, earth abundant. If we expand the discussion beyond the perovskite active layer, and if we go towards the transport layer, the substrate, and the metal contact, then I think it becomes more complicated, obviously. To my knowledge, people are actively trying to replace some of the expensive components, such as gold metal contact, to a more cheaper, such as carbon-based contacts, and also sort of the transport layers that is widely used right now are some of the organic ones, which is more expensive than the inorganic alternatives. So there are some efforts in the community right now that is trying to transition the more expensive material to more, I guess, more economical ones. But at the same time, the efficiency needs to sort of be there. If the efficiency tanks, then it sort of beats the purpose. So I acknowledge that it's a very complicated and tricky task. I hope there's a lot of smart people out there that will do it for me. So yeah.
Great, thank you, Jason. Another question from Stephen. Can you talk about why there is this trade-off between stability and efficiency? If that trade-off exists, do you think there is a way to overcome it?
So currently the trade-off is, so there is a concept called the Goldschmidt tolerance, which determines sort of what cations can form these perovskite crystal structure. And let me just move this. The cations shown here, the Fa and Ma, sort of fits nicely within that tolerance range. However, if we go towards these smaller alkaline metals, then they start to fall out of those tolerance range, meaning that you won't be able to make a, I guess, a stable perovskite crystal that results in high efficiency. However, the unfortunate downside of these organic cations is that they are reported to undergo sort of decomposition over time, especially under light and also when exposed to heat.
Great, thank you, Jason. So we have time for one more quick question. This may be a longer one. The Gretzel group reported high efficiency perovskites with doping, polyamidental doping, without surface passivation layer. With this method, surface defects seem to be passivated, which yields high efficiency. So I guess the question is, how can we differentiate efficiency that results from surface and bulk defect healing?
How do you distinguish the difference between surface and bulk defect healing?
Yes.
So one way, that's actually a very interesting question, because that's something that I'm also thinking about, or I guess constantly thinking about, is when we say that there is a passivation layer, unless we know exactly what we're passivating, it's sort of broadly just termed in. And if you want to sort of really know distinguish sort of the surface passivation and the interface passivation, an experiment they can do is to measure the film property with the sort of the layer, the passivation layer on the bulk perovskite and measure its property. And also you could you could attach a transport layer and measure its property. And if you see a significant improvement in the performance or the film quality, such as the photoluminescence efficiency, when we put the passivation layer onto the bulk, then it's most likely going to be a surface passivation. And if we see an improvement in its property with the whole transport layer or any transport layer on top, then it's most likely going to be an interface passivation. So there are some ways that you could distinguish the surface passivation and interface passivation. At least from our work, we think a lot of the benefit is coming from interface passivation.
Jason, thank you very much for the wonderful talk, the excellent work. I send you a virtual and a physical clap, and thank you for joining us in this very late hour. And thank you participants for joining us in our twice weekly seminar series. And I invite you to join us again, same time, same channel on Tuesday at 11 o'clock. The speaker on Tuesday will be Daniela Espinosa Hoyos, and she'll be talking about engineering myelination in vitro. So I encourage you to stay safe, have a good weekend, and join us for additional intellectual stimulation from our phenomenal students. If you have additional questions, please reach out to Jason. Again, Jason, thank you very much. And everybody else, have a great day.
Thanks, Brian. Bye-bye.